Hello friends, welcome to our YouTube channel Design in VTU, where we help students to understand and apply design concepts in a more simple and systematic way. Here is the next video on design of shafts numerical number 2. So if you are new to our channel, please subscribe and press the bell icon to receive the early notification. So let's get started. The problem here reads like a horizontal piece of commercial shafting is supported by two bearings which is 1.5 meter apart. So here you have two bearings, left bearing and the right bearing, so which are 1.5 meters apart. A keyed gear 20 degree involute and 175 mm in diameter is located 400 mm to the left of the right bearing. So from the right bearing you have a gear and which is at a distance of 400 mm. Directly behind this gear you have one more gear, and he says it is driven by this gear directly behind it. So this gear becomes the driver and this is your driven. Next, a 600 mm diameter pulley is a key to the shaft 600 mm to the right of the left bearing. So from the left bearing you have one pulley and which is at a distance of 600 mm. And directly behind this pulley you have one more pulley. So he says it drives a pulley with a horizontal belt. So this is your driver, this pulley is your driver, and this pulley is your driven pulley. The tension ratio of the belt is 3:1 with the slack side on the top. So this is your T2 is the slack side and T1 is your tight side, and it is on the T2 is on the top and T1 is in the bottom. The drive transmits 45 kilowatt at 330 rpm. Take KB is equal to KT is equal to 1.5. Calculate the necessary diameter of the shaft and angular deflection in degrees. Use allowable stress as 40 MPa and G is equal to 80 GPa. So this is the space diagram what I have drawn. Here you can see the left bearing and the right bearing, and the distance between them is 1500 mm. So from the left bearing at a distance of 600 mm you have a pulley of 600 mm diameter, and from the right hand bearing you have a gear of 175 mm diameter which is located at a distance of 400 mm. So behind this gear, that is 175 mm, you have one more gear. This is the one more gear which is indicated on the right side view. And behind this pulley you have one more pulley, and since it is a belt drive I will not show that pulley. So that according to maximum shear stress theory, diameter of the solid shaft is given by this equation: D is equal to 16 by pi tau ed kb mb whole square plus kt mt whole square root and whole to the power cube root. That is equation number 14.12 volume 1 from Dr. K. Lingaya data handbook. So tau ed is equal to 40 MPa and that is the given data, and kb is equal to kt is equal to 1.5 given data. So straight away from this equation I have this kb, I have kt and I have tau ed, and my next is to find the MT, maximum torque. So the maximum torque, now I will consider a pulley drive at B. So here the pulley at B is a 600 mm diameter pulley, so therefore I can write the equation MT is equal to T1 minus T2 into RP1. So since the given condition is T1 by T2 is equal to 3, so therefore, and also given the condition is N is equal to 45 kilowatt and RPM N is small n is equal to 330 RPM. So these two are given data. So I can write the equation from the data handbook 2.87b volume 1, that is MT is equal to 9550 into 1000 by into capital N by small n. So once I substitute the capital N and small n, I'll get the maximum torque as 1.302 into 10 power 6 Newton mm. So I substitute back into the equation MT is equal to T1 minus T2 into RP1. So here RP1 is the radius of the pulley. So the diameter is given as 600 mm. So RP1 will be 300 mm. So coming back into the equation, so the MT we have found as 1.302 into 10 power 6, and T1, since the condition is given T1 by T2 is equal to 3, so therefore I can write T1 is equal to 3 times T2 minus T2 into 300. So upon substitution, I will get a T2 is equal to 2170 Newton and a T1 is equal to 6511.36 Newton. So from the diagram here, I have a shaft and I have a pulley of 600 mm, and behind this I have one more pulley, and this is the side view. So this hatched one is the design shaft, So from this diagram, the total vertical force on this shaft will be 0 because the weight of the pulley is not given. Total horizontal force, so T1 by plus T2 is equal to 6511.36 plus 2170.45. So here the total horizontal force will be 8681.81 newtons, and which is going behind. So the direction is indicated here. So if I see it from the right view, so it will be going to the right side. Now consider the gear drive at C. Here we know the torque mt is equal to Ft into Rg. Since the gear and pulley are mounted on the same shaft, the torque remains same. So therefore I can use the same equation, same value as of mt, 1.30 is 6 into 10 power 6. Since Rg, the radius of the gear, that is the diameter of the gear is given as 175 mm. So therefore the radius of gear will be 87.5 mm. So therefore upon substitution, I will get the tangential force Ft is equal to 14925.71 newtons, which is tangential force. Similarly, I can find the radial force Fr is equal to Ft into tan phi. So upon substitution, I'll get the radial force as 5432.51 newtons. Now let me draw the diagram. So here, this on the left is your driven gear, and which is the shaft to be designed. On the right you have the pinion or the driver. So the driver pinion is, the direction is counterclockwise. How did I get this counterclockwise direction? So let us come to the diagram. So here he says, look at this diagram, the pulley drive. So here he says the slack side is on the top. So when in what condition will be the slack side on the top? So definitely if the this pulley will rotate, has to rotate in the clockwise direction, then the tight side will be on the bottom and the slack side will be on the top. So when this slack side will be on the top, so this pulley will rotate in the clockwise direction. So this pulley will also rotate in the clockwise direction. So since this gear is located on the same shaft, so that will also rotate in the clockwise direction. So behind this gear you have one more gear, and that will rotate in the counterclockwise direction. So therefore I have taken the direction of the driver, that is the gear, as the counterclockwise direction, and the gear which is mounted on the shaft to be designed in the clockwise direction. So therefore, coming to the diagram here, so therefore here the pinion or the driver which is behind the shaft, it is the driver and which runs in the counterclockwise direction. So the tangential force will be in the upward direction and the radial force will be towards the center. Next, on the design shaft, so since it is the driven gear, and the tangential force will be below, and here the radial force will be acting towards the shaft. So therefore from the diagram, so here from the diagram, the vertical force on the design shaft will be 14,925.71 newtons, and the radial force will be 5432.51 newtons. Same will indicate on the VLD diagram. So here you can see the vertical force at pulley B will be equal to 0, since the weight of the pulley is not given. So therefore the vertical weight force on the pulley will be 0. At gear C, the tangential force is acting downwards. So here you can see from the diagram that this tangential force Ft1, here it is indicated, and that is acting downwards. So that tangential force Ft1 is indicated here, 14,925.71 newtons in the vertical load diagram. Next, coming to the horizontal load diagram. At pulley B, so you can see here the pulley B here, the horizontal force is T1 plus T2, and that force are going away from the observer. If I assume that the observer is somewhere standing here, so therefore these forces will be going away from the observer if I see it from the front view. So therefore those two forces, that is T1 plus T2, will be 8681.81 newtons, and that is drawn upwards on the shaft. So please note here, any force which is going away from the observer, in case if the observer is standing in front of the shaft, so those forces will be drawn on the shaft upwards, and any force which is coming towards the observer will be drawn on the shaft. So here we can see the HLD diagram. Here we can see the HLD diagram, and at gear C, so the radial force, here you can see the radial force which is coming towards the shaft. This is your radial force FR1, and that is coming towards the observer, so this is indicated on the shaft at 5432.12 newtons. So that is your HLD diagram. Now from the VLD diagram, let me take the moments. Taking moments about A, I can write that RdV into 1500. So these forces in these moments will be taken as a positive, and this will be taken as a negative. Any counterclockwise will be taken as positive, and any clockwise will be taken as negative. Here this RdV into 1500 minus 14925.71 newtons into 1100. Therefore I can get RdV is equal to 10945.52 newtons. Similarly, if I take the moments about D, so these moments will be taken as a positive, and these moments will be taken as a negative. So therefore RAV into 1500 minus 14925.71 newtons into 400. So therefore I can get RAV is equal to 3980.18 newtons. So similarly from the HLD diagram, so taking moments about A, RDH into 1500 minus 54321. So these will be considered as positive, and these will be considered as negative. So therefore RDH into 1500 minus 5432.12 into 1100 plus 8681.81 into 600 into 600 will be equal to 0. So therefore upon solving, I'll get RDH value is equal to 510.83 newtons. Similarly, if I take the moments about D, so therefore the RAH value, this is taken as a positive, and these are taken as a negative. So therefore initially RAH is considered as from the downwards. Initially this is the position of your RAH. So therefore RAH into 1500 plus 8681 into 900 minus 5432.12 into 400. So therefore upon solving, I'll get RAH value is minus 3760.50 newtons. Since it is a negative value, I will shift that force from the upward direction. So therefore the direction of RAH will be changed here. So now coming to the VBMD, so therefore I can write the bending moment at A is equal to 0, bending moment at B is equal to 2.378, bending moment at C is equal to 4.38 net per 6 Newton mm, and bending moment at D is equal to 0. Similarly, if I want to write the HPMD horizontal bending moment diagram, bending moment at A is equal to 0, bending moment at B is equal to minus 1.95 10 power 6, and bending moment at C is equal to 0.204 in 10 power 6 and bending moment at D is equal to 0. So finally we will draw the resultant bending moment diagram. So therefore at B you have the value as bending moment, resultant bending moment value is 3.076 into 10 power 6, and the maximum bending moment at C it is 4.384 into 10 raised 6 Newton mm. So that is your maximum bending moment. So now let us put back all the values into the equation. So therefore I'll get the bending moment, maximum bending moment as 4.38 into 10 power 6 Newton mm. So upon substituting in the equation D is equal to 14.12 equation, I'll get the value D is equal to 95.5 mm, and which is approximated to 100 mm, and this is the recommended diameter of the shaft given in the table 14.6 volume 1. So that is the solution for the diameter of the shaft. Now let us find the angular deflection theta. So here we will use the equation 14.17 from the volume 1. Here the diameter of the shaft is known to us 100 mm, so that is being substituted. So G, we know that it is 80 GPa, and L, it is the distance between the pulley and the gear drive. So therefore I'll get L is equal to 500 mm. So upon substitution I'll get the value as theta is equal to 0.047 degree, that is the angle of deflection. So that is the solution for the complete problem. Please subscribe and share with your friends. Thank you for viewing. Happy learning.